Welcome to my lecture this evening. I know it's been a busy day for everybody, so thanks for those who've been able to make it. I think there must be a lot of tired people out there. I'm going to talk today about time, which is something that we all take for granted, but maybe it's not as simple and straightforward as it first appears. So I'm going to use, just by way of making it fun, there's actually a British comedian called Diane Morgan, and she has this alter ego called Philomena Kunk, and she does this, if anybody's seen it, I think it's hilarious, and she does this little piece where she pretends to not be very intelligent, and she interviews astrophysicists and all sorts of people as though she's a 4-year-old. And I've got 3 clips of her because she did a show on what is time, and so I thought it was appropriate, and I'm going to intersperse it. It's very British humour, but I'm sure you'll get it. So let's start off. Everybody went to school, and everybody did math at school, and this is what we're told. So speed equals distance over time, therefore time equals distance over speed. So a car doing 60 miles an hour, in an hour it goes 60 miles. So very simple, very straightforward, and we all understand that. But if you apply it to time in our lives, so this is me with the red circle round. There's 2 things here. I started with the quote, Salvador Dali quote, I am not strange, I'm just not normal. And at my school, all these boys wore a white shirt and a tie. You could wear a blazer or a sweater, but I refused to wear a tie and had a different shirt and a different jacket because my mom said I didn't want to look just like all the other boys. So nothing's changed. Nothing's changed. But it was about this photograph was taken about 59 years ago, and about 8,000 miles from here, and and I'm currently standing still, so I'm doing 0 miles per year. So speed equals or distance over time doesn't work when you apply it to yourself, right, or to your past. It just doesn't work. And so that's really the principle of what I'm going to talk about. So we've got a few minutes, so I thought I'd do a brief history of all time, and this is using a Philomena Kunk quote. Just by the way, is there anybody here from Plymouth? Then maybe I should move on. Maybe I should move on quite quickly, but no, I won't. Let's just listen to Philomena Kunk.
It's hard to imagine while you're standing in it, but there was a time before Britain, before Europe, before the world, even before the universe. Nobody can say when it was, because it was also before clocks and words. It was a time when nothing existed, empty, without motion or energy or light or hope, just like Plymouth today.
Yeah, well, but you get a sense of humor, right? But this is a brief history of time. So these are sort of things that we know. So generally, there's a view that time sort of travels in one direction. We'll come back to that a few times. But this is like looking at the history of the universe from the first moment of the Big Bang. And I'm going to finish by sort of, really questioning whether that was the beginning. But what happened, there were particles that came out, mostly photons, in the first few seconds. It says the first microsecond, and then we believe that's what the Large Hadron Collider in Switzerland is doing. Is trying to establish, well, it has proved that the Higgs boson particle that was theorized actually exists, and that is the particle that gave light mass. And equally, last week, scientists in Italy, for the very first time, they actually froze light. They actually froze it. So, but let's not digress there. This is what happened. So the particles receive mass. So we got helium and hydrogen. We know the periodic table: hydrogen, helium, lithium, beryllium, boron, carbon. I'm sure you can quote it as well as I can. Maybe not. But anyway, maybe you can. And then the first atoms formed, and then the stars were created, and galaxies and dark matter. We don't know what dark matter is, but we believe that it's more than 85% of the universe comprises a matter that we can't see, so we call it dark matter, and it holds things together. And dark energy is why the universe is expanding faster and faster. So that happens about 10 billion years, and we think the universe is the best part of 14 billion years old. So that's the history of everything that we know. And I'm going to come back to a few of these things as we go, but I wanted to put that up as a framework. So in terms of time, we experience everything from our own perspective, and I'm going to give an example of this. Did everybody look on this morning, see the rainbow on the port side of the ship? You saw it. What shape is a rainbow? It's an arch. It's a circle. It's a circle. Rainbow is a circle. So we look at rainbows like this, and we know that rainbows are refracted white light splits into its primary colours, and we can see a rainbow when the sun is behind us. So that's how we experience a rainbow. Rainbows actually look like this. So they're actually a series of infinite number of circular loops, only a few of which are in the range that we can see. And of course, we see them from Earth. They look like they disappear beyond the horizon. Bad news is there is not a pot of gold. At the end of those rainbows, they are simply refracted light through the air. We see them from our perspective, so we start to believe that those things are the arches that we see. I took a photograph too, but if we had an aeroplane and flew over, we would see that they're circular. So, you know, it's what I was saying the other day is, you know, we have to sort of don't believe what we think. You have to, you know, that's the case of where we are. What I'm going to talk about is sort of the limit of science, and that requires us to not always believe that what we think to be true is actually true. So let's talk about time. So time is, we believe there are three parts to time, and we believe there's a past, a present, and a future, and the present is often referred to as now. So I'm going to start with Diane Morgan, or rather as her alter ego, Philomena Kunk. She's going to interview for about a minute or minute 30 seconds somebody whose whole life is about saying what time is. Have a listen to this.
One science man who knows all about time is this science man. Hello, science man, who are you?
I'm Dr. Stuart Clark. I'm an astronomy writer and a fellow of the Royal Astronomical Society.
What is time?
We don't actually know. There are a couple of possibilities. Either time could be a physical thing that flows like a river, or it could be more of a psychological thing.
When you say it's like a river, what do you mean?
I mean that time flows like the water in the river, and that the events in our lives are like things in the river that water encounters.
Like fish and stuff.
Yes.
You know when you store time on a clock, how do you get it back out again? Because when I was winding my watch up, I accidentally put it forward, so I'd got 2 hours more in my clock. But I put it back, but I thought, is it still in there? Is the time still in the clock?
So your watch doesn't actually measure time?
Well, it does, because it's accurate.
It measures the oscillation of a crystal, and the change in the physical state of that crystal has to happen in what we call a certain amount of time. So from one moment to another, physical systems everywhere in the universe changes its state, And that change takes place in what we call time. And that's the only way we can infer the existence of time. But actually what time is, we don't know.
Right. So even the people who understand time don't understand what time is. It'll always be an unknowable mystery.
Yeah, crazy, but I mean, that guy is an expert on time. But you see how difficult he finds just with her simple probing questions to explain what time is. So we should have a go at it. So first of all, we're traveling mostly in a westerly direction, broadly in a westerly direction, through a series of time zones. So here's the world's time zones put on a map. I made it to the world is not flat, just in case you're wondering. I just put it on a 2D screen. Here's the world's time zones, and you can see they make no sense whatsoever, right? I mean, they're nonsense. So if you look at them, these are the direction of time zones. They basically follow the borders of countries. Greenland is in one time zone, but maybe it should be in two. And China is in one time zone, and it should be in, well, at least three. And the time zones step India, we know about the half-hour time zone in India. So it doesn't make any sense at all. But just as an example, because the Earth is actually a sphere, all these time zones that go broadly north and south, they meet at 2 points, one in the north and one in the south, right? And we call those the poles. So if it's midday today here on the east coast of Africa, if it's midday, what time is it at the North Pole? What, midday, do you say? Whatever you want. Yeah, that's the right answer. Whatever the time at the pole is whatever you want. It's every time at the same time. Because it doesn't matter. The time zones don't matter. They're simply a construct to follow the pattern of the rising and the falling sun. They don't make any sense whatsoever when we join them together at the poles. Yet we rely on them. Even more ridiculous, just as a simple example that proves sort of how this works. You remember this quote? Who was it now? Oh yeah, that was it, Sarah Palin. You can see Russia from here. Yeah, I just stole that just as a bit of fun, but it's sort of true, right? She was right. I mean, we all know Sarah Palin was right. Yeah, Sarah Palin was right. So this is, of course, these are Diomede Islands sit there in the Bering Strait, and that's where they are on a map of the Earth, and they look like this. So there are two islands, one owned by Russia, and one belongs to the United States, and they are 2.4 miles apart. And the sea between them freezes at certain times of the year. That won't be the case in 100 years, but they currently, the sea between them freezes, and you can walk between the two islands, and you can see Russia from the United States on that island. But here's the international date line. They are 23 hours apart. So you can walk from one island to the other and travel in 2 miles, travel 23 time zones. And so if anybody says, can you travel forward in time? The answer is yes. You just go to these islands and travel between the two. And you can also travel backwards in time. So it sort of doesn't make sense, right? The sun rises pretty well and sets at pretty well the same time in both places, almost exactly, and yet they're 23 time zones apart. So I'm really talking about this to sort of show that time that we come to rely on, it's not as obvious what it is as we may initially think. So let's have a look at time in our solar system. So how do we measure how old we are? Trips around the sun. So if we were to go on trips around the sun on other planets, how old would we be? So here, this is the example. If we were 25 years old on planet Earth, I wish. If we're 25 years old on planet Earth, what age would we be on the other planets? And you can see a 25-year-old on Earth would be over 100 years old on Mercury, and yet would be only a fraction of a year old on the other planets, because the speed at which they travel around the sun is completely different. Another measure of time is that, does anybody know what year it is today? This now. 2025. Well, that's sort of true. It depends where you are. So these are the years, what the year is in different countries of the world. And so 2025 is mostly true for people who follow the Roman calendar. People who didn't follow the Roman calendar, the year is completely different. Places like China adopt the calendar the same as us, simply for the case of doing business, because all of their invoices would be dated, 2000 or 4722, and probably get rejected by every payment system. So they adopt 2025, but it's different in places. It's different in India. It's different in throughout North Africa, because they don't follow the Gregorian calendar. But even the Gregorian calendar is a problem. So this is the calendar that we follow, but in Roman numerals, what major number is missing? No zero. So there was no year zero. It went from 1 BC to 1 AD we'd missed out the zero. And so the consequence of that is that Prince was wrong. We didn't party like it was 1999, because it wasn't. And the missing zero is that the millennium didn't actually start till January the 1st, 2001. So we come to rely upon these things. We believe they're really true when they're not. Time zones make no sense. The year that we're in makes no sense. You can travel forwards and backwards in time by walking between two places across the time zone. So that's one thing. Another is this, we probably all feel this. Does time go faster as you get older? So my friend says time is like a roll of toilet paper. The closer you get to the end, the faster it goes. Sort of true. And the reason is that the answer is yes. Time seems to go faster as you get older, because a year is a smaller proportion of our lives than it is when we're young. And so the consequences of that is they just seem to pass faster. And there have been a lot of studies about this that people say time seems to go quicker as I've got older. And that's one reason that says that's true. And it's not just anecdotal. We also make memories. Memories seem more significant when we're younger than they do when we're older. So they have a bigger proportion of our lives. They seem to have a bigger impact than they do when we're older. So it does seem that as we experience time, it appears to go faster when we're older than it does when we're younger. I mean, our childhood seemed to last forever, but the years, my birthday seems to come round every 5 minutes these days. So it just seems to be how it is. Another thing is, a third of our lives-ish, we're asleep. Why don't we experience time when we're asleep? I mean, when you wake up, the first thing you do is you look and you say, what time is it? You have no idea what time it is, right? Why? Why? Because you're sleeping. But time doesn't stop, does it? Why we don't experience time when we're asleep. So when we're asleep, there are various stages of consciousness, right? So this is wakefulness versus awareness. The worst place is a coma, right in the bottom corner, right? So there, we're not aware and we're not awake, and we're in a coma. Then there are various types of sleep. There's REM sleep and deep sleep, and drowsy sleep and dreams and all these different things. But we don't experience time when we're asleep. And the reason is, I'll try and explain it. So first of all, can we actually go to the past? Only in memory. Well, could we actually travel to the past? Could I go to the past? I could never go to the past. Could I go to the future? No, I could never go to the future. So the present, or now, is the only place that I can be. And how long does now last? How long does it last? A second? Forever. So it's everlasting, right? So the present is everlasting. Time is just an everlasting present. The past is just a construct. Everybody's experience, even going today on safari, everybody's past is different. If everybody got questioned on how their experience of today, it would be different. And the future is just completely unknown. So it goes from order to chaos, and it passes through now. And now is the only thing that is important in our lives. It lasts forever. So say now is eternal. Eternal meaning it's ever present. The past is not a reality. The future is a prediction. And as I explained the other day, our brain is not a computer. Our brain is a pattern recognizing part of an organ in our body. It doesn't do any calculations. It recognizes patterns. And so when we're asleep, our only experience of time is life filtered through our brain. That's our only experience of time. And when our brain is resting, we can't experience time. So for a third of our lives, we have no idea what time is. So in terms of, like we just said, we can't go to the future, but could we travel through time? The question is, according to Einstein, so Einstein's general and special theory of relativity actually says we can travel into the future. And the reason for that is if we took a clock and we speed the clock, we make the clock travel at close to the speed of light, time stands still. It stands still for the clock. It doesn't stand still for the observer of the clock, but it stands. So light does not experience time. It's only things with mass that experience time. And depending on the mass, we experience time differently. So according to Einstein, we can actually travel into the future, and we do travel into the future. I'll come back to it later, but every satellite that circles the world travels at its clock is different to what it would be on Earth. And all of our GPS systems depend upon us making an adjustment based on Einstein's equations. Otherwise, we would all be in the wrong place from our GPS. So we sort of know that we know that Newton's laws of gravity work at very low speeds. We know that Einstein's special theory of relativity works at very high mass, but they don't make sense of the universe. So time depends on our speed. Somebody beforehand was asking me about this. If you take two clocks and one is moving relative to the other, then according to Einstein's equations, the moving clock will appear to be slower than the stationary clock. And this is something called time dilation. So this is the definition of time dilation. It's the difference in time measured by two clocks because of their relative velocity, or the difference in gravitational potential. I'll come back to that. But depending where you are, if you're on a large star with a heavier mass that has higher gravity, then the clocks will move at a different speed altogether. And this is how our GPS systems are adjusted. It says time goes slower at the International Space Station, lags about 0.01 seconds for every 12 Earth months. Now that's not much, but in 25,000 miles around the Earth, it's enough to put us significantly out of position if we didn't make the correction. And the same issue of speed, time moves differently depending on your speed, also applies depending on your gravity. So if you're on Jupiter, this is how fast you age after 30 years in these places. So it's minus 18 seconds on Jupiter, plus 691 milliseconds on the moon. It's different at the top of Mount Everest or at the bottom of the deepest ocean. So the gravitational force on Earth is not the same. It depends on the altitude, and we make an approximation. We say the acceleration due to gravity on Earth is 9.81 meters per second, or about 30 feet per second. But that's only true on average. It varies depending upon where you are. So your watch moves differently at the top of Mount Everest than if you were diving underwater in the deepest trench. And so you could travel through time. So then the astronauts go out, if they go out to the moon and come back, people have aged more than them. There is a time difference between how much they've aged and experienced time versus the people they left behind on the Earth. And the further we travel, the bigger that gets, the bigger that issue gets. There's an issue whether could we travel backwards through time. So we all know that apparently Back to the Future, this is the DeLorean that traveled through time. The question is, could you travel backwards through time? And so in order to do that, you would have to travel faster than the speed of light. And the current laws of physics are that you cannot accelerate something to travel faster than the speed of light, and anything that has mass cannot be accelerated to travel faster than the speed of light, because to travel at the speed of light would require an infinite amount of energy in order to do so. However, Einstein's special theory of relativity also says if something is already traveling faster than the speed of light, it takes an infinite amount of energy to slow it down to the speed of light. But it is allowed to travel faster than the speed of light. So something that travels faster than the speed of light we call a tachyon, and we're not aware of anything that we can understand as a physical reality that explains a tachyon. So it's one of those things that exists in mathematics, but we could not ever find a way, or we cannot imagine how you would ever find a way to show that it exists or how you would measure it. It's because it's not physical reality as far as we're concerned. And I'll come back to that because it's back to the Big Bang and the question of was that really the beginning of time? The other possibility, which you see on a lot of science fiction films, is this. It's called the Einstein-Rosen bridge. Rosen was Einstein's assistant in a lot of his experiments back in the early part of the last century. And you don't need to read all of that on the screen. It's just the description of what an Einstein-Rosen bridge is that it's a wormhole. So effectively, it's a hole through the space-time fabric that allows you to travel extreme distances. The way to think about it is if the universe was a sheet of paper and you folded it over, those two ends of the paper that were far from each other would then touch and you could travel between them. And that's the notion of what a wormhole is. So Einstein said space-time is a fabric, and if the fabric sort of folds on itself, you get a wormhole. And we imagine they look something like this, and it's wrong. This is wrong for many reasons. One is that space-time is not a two-dimensional fabric, but we like to visualize it that way. Evidence whatsoever that wormholes actually exist. They're theorized that they might exist inside black holes, but we have no way of ever looking inside a black hole. So, currently, on the basis of our science, we will we will not know unless we get some new science whether these things are actually true. We measure extremely large distances by using light years. I just find this sort of funny. I put this at the bottom. It really makes me laugh that when we got the motor car, we measured the power of the car using horsepower because we'd had horses, and we still measure the power of the space shuttle using horses. So we say the space shuttle has 37 million horsepower. It's the biggest nonsense. I just find that sort of hilarious. I think it's science having a laugh at us. But of course, we're on this ship, and the ship speed is measured in knots, and so are aeroplane speeds measured in knots. Knots was the speed at which the knot in the rope was let out by the guy on the ship to measure how fast it was going, and we still use that as a unit. And even earthquakes measured in sticks of dynamite. Earthquakes, and compare them to a stick of dynamite. It's funny how these things sort of stick with us, make no sense. But we measure distance using light years. But does anybody know what a light year is? The distance light travels in a year. How many miles is that? 186,000 miles per second every second for a year. So I did the calculation because it's not easy to do in your head. It's 6 trillion miles. So 1 light year is 6 trillion miles, and we measured that. So and so we've got 2 questions. One is, how do you measure the speed of light? And secondly, what if light has a finite speed? So the speed of light is finite and limited to 186,000 miles per second, but the universe is infinite, we think. And so we've got finite speed in an infinite universe. And what that means is we don't see things as they are, we see things as they were. So interesting, I'm going to do a talk on astrophysics. I'm not sure, we haven't got the schedule for the rest of the talks, but part of it is that if you can imagine, I'm going to talk about the search for extraterrestrial life, but one of the questions is, if there was a life out there that was 65 million light years away from us, and they looked at us through their telescope, they'd see the dinosaurs. So if they were looking for us, we're not there to be seen, because the light takes 65 million years to get there. And so they see us as we were and not as we are. And that's part of the problem of searching for life on other planets. And equally, if they saw us, if they saw the dinosaur and they said, "Hello, dinosaur, how's life down there?" That would take 65 million years to ask the question, and then the dinosaur would shout, "We're going extinct," and they'd hear that 65 million years later. So that conversation would take 130 million years. So it's not very good dinner conversation if it takes 130 million years. So because light has a finite speed. The question of why is there a speed that we cannot exceed? It's very difficult to explain. Speed of light, as I explained, is this. Just give you some sense of it. It takes about 8 minutes 20 seconds for the sun's light to reach us. So if the sun went out, we wouldn't know for 8 minutes 20 seconds that the sun had exploded. Then we would. And light, the Milky Way, which is 100,000 light years across and only 1,000 light years deep, it's got a ratio of 1,000 to 1. So it's a flat disk to all intents and purposes. It would take 100,000 light years for light just to cross the Milky Way, and the universe is expanding faster than the speed of light. But you said nothing can go faster than the speed of light. Yeah, I did. And the reason that the universe expands faster than the speed of light, well, first of all, this is why we can't have a speed faster than the speed of light, because by definition there is no speed faster than the speed of light. It's like saying going to the North Pole and asking which way is north. There is nothing beyond that. but the universe is expanding faster than the speed of light, because if two cars moved away from it, it's expanding like a balloon, and every point on the surface is expanding. And if two cars doing 30 miles an hour drove in the opposite direction, after 1 hour they'd be 60 miles apart. But if the speed of light was 30 miles an hour, they would have traveled twice the speed of light in theory. It's just simply that the expansion is causing things to move away from each other faster than the speed of light. I'll come back to that later. We know the speed of light. We've been measuring it for about 400 years. So this is the first measurement. These are the actual original calculations of the first measurement, which was looking at this planet, this rock Io, as it went around Jupiter, and measuring the time as the Earth had moved. These were calculations that were done, I think, in 1650, something like that. Measured the speed of light. There have been lots of measurements, different measurements that have taken place. At the top, you can see from 1676 to 1983 how the speed is sort of originally, they thought it was 220 kilometers a second. Now it's 220,000. Now it's pretty well 300,000 kilometers per second. And this is a graph that shows how, we're now pretty convinced by a whole range of different things, rotating mirrors and all sorts of things that have been used to measure the speed of light. We're pretty sure that is the speed of light now. Why light travels at that speed, we don't know. So we know that it does. We don't know why it does, but it's a fundamental constant of nature. And as I said in my last presentation, light travels 1 million times faster than sound. And so even as you're watching me now, everything that you see occurred later than everything that you hear. So your brain puts together what you see, my lips moving, and what you hear. They don't occur at the same moment. It's aligned in your brain. I already explained how the universe is expanding faster than the speed of light, and that's simply because we've got these points moving apart from each other. The universe is now 90 billion light years across, but it's only 14 billion years old. So it's clearly been expanding nearly 7 times faster than the speed of light when looked at it that way. But there is no mass that exceeds the speed of light. But a consequence of the fact that light from a star that's expanding faster than the speed of light, it will never reach Earth because it's moving away faster than the speed of light. The light will never reach us. That's a very difficult concept to imagine, but because it's moving away at that speed, the light will never ever get to us. And so what will happen over time is the sky will go dark. Stars will just start to disappear because their light will never reach us. And this is as good as it gets for stargazing. There's only ever going to be less stars to see. It's a pretty depressing thought, but true. So what is gravity? And again, spoiler alert, we don't know. So gravity, I explained briefly earlier. Gravity, Newton said gravity is a force between two objects. Einstein showed that's not to be true and said no, gravity is space and time are connected to each other in what he called space-time as a fabric. It's a 3-dimensional fabric. We imagine it as a 2-dimensional fabric because our brains can't imagine it otherwise. And when you put a mass, it's like a big trampoline. When you put a mass in the middle of the trampoline goes down, and that means that anything that goes along the trampoline goes down around the mass, and that going around the mass is gravity. That's what Einstein said. So it's looked at like this, and so that space has 3 dimensions, and time is the 4th, and gravity, if this is planet Earth and that's our moon, they have different gravities because they have different masses. So small mass, small gravity, big mass, big gravity, and that generally works. I mean, most of Normal experimental physics shows that actually to be the case, and in looking at space-time, the idea is that we look at it like this. So this is now. The red dot is now, and the past is a cone that sits behind us, and the future is a cone that sits ahead of us. And sort of for most of my life, this has been the belief of where physics is in terms of understanding space and time, 3 dimensions in time. We have no way we can mathematically describe a 5th dimension, but we have no way to visualize it. And we can mathematically describe space-time in 3 dimensions, but we have no way to really visualize it. And so in the last couple of minutes, last 5 minutes, I want to just talk about, I'm trying to give you the present state of science. So right now, a bit like with artificial intelligence, everything we know is changing. So we've got this issue of quantum mechanics versus the theory of relativity, which I called, as a sort of movie title, The Battle for the Universe. So we sort of know Newton applies at low speeds, Einstein applies at high mass, but in terms of quantum mechanics, what we're finding from the quantum mechanics experiments is that time is not a universal rhythm. It is not a flow from the past to the future. It does not flow in one direction. We know that the faster a clock moves, the slower that time passes. But we also know that there are things we don't know, and we can measure them. The first one I put in yellow is quantum entanglement. So we know that if you tangle 2 electrons, and you put them, let's put them 100 million light years apart, and you observe the spin of 1 electron, and every electron in the universe is the same. We've never found an electron that's different. If you observe the spin of that electron, the other electron will be the opposite. And if you change the spin of this electron, the spin of the other electron will change instantaneously, even though they're 100 million light years apart. Impossible to imagine that, but it's true. What has also been understood is the Schrodinger's cat experiment that I talked to you about. There's cats in a box. Until you observe it, it could be alive, it could be dead. When you observe it, you know whether it's alive or dead. Prior to that, it exists in both states. What is now believed is that the act of looking at the cat and quantum entangles us with the cat. And so somewhere else, if the cat, when we open the box, the cat is alive, somewhere else, the cat is dead. And they occur at the same time, because that is why the act of observation determines the state. And so for a long time, it was a belief those things were not connected. Now we believe they are absolutely connected, and we are just a fundamental part of the universe. And I'll explain what that means in terms of time. The other things we don't understand, which we believe play into this, is dark matter that is basically a gravity that we have not been able to understand what it is, that glues the universe together, and dark energy that causes this expansion faster than the speed of light. So Einstein described it as this: spooky action at a distance. But separated objects, no matter how far they are, share a condition or state. And we quantum entanglement, we know, we're absolutely certain it's existed and it's real, and every experiment in quantum physics proves that it exists, but we don't know why, and we don't know what it means. This is the Large Hadron Collider, and this is where the experiments are being done to determine this. But what the current state of thinking is that it's believed that the Big Bang had an equal and opposite situation, and that there is another place, I don't even know how to describe it as a place, but there's an opposite situation in which time goes backwards. We are in a place where time goes forwards, and there's an equivalent that is a quantum entangled version of us, where it goes in exactly the opposite direction. Very hard to imagine that, but none of the quantum mechanics, when applied to that idea, every equation works every time. So there's been nothing, all the experiments that are done here have really understand this quantum paradox of negative time. So it's sort of, the belief is that time is an illusion that stems from quantum entanglement. It's our experience of time going forward, but there's somewhere else where, I don't even want to say somewhere, I don't even know what the word is for it, but there's an opposite situation where time goes backwards. So when we break an egg, and so we go from this order, so the past, we go through order, present, chaos. That's the sort of way time flows. The future is unknown, but the past is known, and now can influence the outcome in the future. That's how we envisage it. There's an opposite version of that, where the eggs unbreak, and the coffee and milk unmixes, and things move from disorder to order. And it believed that everything in the universe is quantum entangled. So, we look at this and we say that this mess of blocks, this is, my granddaughter does this all the time, this mess of blocks, it looked like I build that, she does this. And we see that order to chaos is the order of things in our world. But there is a world in which it goes from chaos to order. And some of the experiments that have been done, this is from the 1990s, where photons were fired through what is called a wave packet, and what happened was that the photons emerged before they entered the wave packet. So this was the first observation that looked like something had gone backwards in time. And since then, this has been proven that this is like a car leaving a tunnel before it drove in. And this observation has been found a number of times at CERN. And so the question is, when we think about what time is, it will only ever be our experience of time. In quantum physics, there's an effect occurs in one place that alters the state of something in another place, and that's the equal and opposite to the one that we experience. And so, to bring us to the end, our experience of time is very subjective. It's limited to our sense of now. There is these entangled relationships between objects that suggest that there are other things happen. When we see something, the arrow of time can go backwards as well as it goes forwards. And our memories are based on this steady march of entropy, which is this idea of going from order to disorder. But the one thing I am certain about is that time is precious, and so I'm going to finish my lecture in the words of Diane Morgan, and then we can use the time that's left to go and have some dinner and think about this. Here we go.
Time is precious, but it's not like other precious things. You can't hold it like a necklace or taste it like money.
Like money. Thank you.